the last of the examples that I want you to look at. Simple example, but very, very important example that will give us a lot of insight. So, example number 5. Okay, we are given that x of k is equal to the DFT of x of n. Slightly different notation. Okay, normally we would have written it with the following manner: x of n DFT x of k. Okay, but we are writing this as an equivalent representation. Okay, this as an equivalent representation. The first thing that I want you to evaluate is what is the sequence you get when you take DFT of x of n. Okay, DFT, I hope you are following. I have a sequence x of n, I take its DFT and then I take its DFT a second time. Okay, so the first time, what do you get? This becomes x of k. When you take the DFT a second time, okay, remember the property of duality. So, what this will produce for us will be n times x of minus k modulo n, okay, by the principle of duality. Okay, the first DFT produced for you x of k, you take it a second time, then what you can treat it as some sequence x1 of n, and then basically you will get these are the samples that we will get. Okay, now second question, part B. What do you get when you do the following operation? DFT of DFT of DFT of DFT of x of n. 4 brackets are closing. Okay, so up to this point we have already evaluated the second bracket. This is n times x of the index, it doesn't really matter, so you can call this as minus n modulo n. Basically, it's an index that goes from 0 to n minus 1. We will call this as x1 of n. Okay, so then what we get is DFT of x1 of n. Okay, this is what we have. This we know what the answer is from part A. This will be n times x1 of minus n modulo n. Am I correct? So basically the same first step will be x1 of k, second step we will get the duality relationship. And what is x1 of k? X1 of n, x1 of n is n times x of minus n. So minus of minus becomes, so this becomes n times x of n. Okay, or in other words, n squared times x of n. So you take the DFT twice, you get a scaling of n with the indices which are time reversed. You take 2 more times the DFT, then the scale factor becomes n squared, and then you get back the original sequence. Okay, interesting property. Again, it's something that once you are able to visualize it, it is something that we can leverage in a very nice way. Now, I want to quickly summarize the convolution using DFT. Okay, so here is the a property that I want you to visualize. If I have a 6-point sequence 1 1 1 1 1, another 6-point sequence, same 6-point sequence, one is x1 of n, the other one is x2 of n. I do linear circular convolution. What do I get? I get 6 6 6 6 6 6. We know how to verify that. So basically, do the circular convolution, write it in the form of a matrix. You will get this. Now the same thing if you append 5 zeros to the sequence and then do circular convolution, then what you get is the linear convolution, okay, by adding 5 zeros. Now, here is the important theory that or the sort of context in which we are looking at it. Supposing you had x1 of n, it had length L, x2 of n had length p. Okay, and I want to do the linear convolution of x1 of n convolved with x2 of n. What is the length? The length will be equal to L plus p minus 1. Okay, so if I have length L and I want an output which is L plus p minus 1, then what I need to do, I must do zero padding. How many zeros? In this case, I must add p minus 1 zeros. Then what I will get is a sequence of length L plus p minus 1. For the second one, the length is p, but I want L plus p minus 1. So what I must do is zero padding of L minus 1 samples. So eventually the sequence will become L plus p minus 1. Once I get this and then I do the circular convolution, then I will get the output as the linear convolution. Now, what if in this particular case I don't add sufficient number of zeros? What will happen? Okay, let's take a good example. Okay, we know that x1 of n has 6 samples, x2 of n has got 6 samples, and the linear convolution should produce 11. But I'm going to add only 4 zeros. That means I will get a sequence of length 10, the original sequence x1, all ones, then 4 zeros appended, length 10 sequence. Do a circular convolution of this 10-point sequence with the 10-point sequence x2 of n. What you find is the output is the given here. Compare it with the linear convolution. You find that there are many samples that are equal to the linear convolution. However, the first one does not match and the last one is missing because you took one less length. So what we can say is, if you choose the number of zeros to be added, okay, let us say that number of zeros to be added. Okay, so if the number of zeros to be added is not correct, okay, what we mean is n is not equal to L plus p minus 1, then there will be some error, samples in error. Some samples in error. How many samples are in error depends on how much shortage that you have. Okay, so supposing we take n equal to, in this particular case, the linear convolution, this was equal to 11, but we chose it equal to 10. Okay, we chose the circular convolution to be equal to 10. What we find is that the number of samples that are in error is exactly short by the sample, the number of the shortage with respect to n. Number of samples in error equal to 11 minus 10 equal to 1. Okay, if you were short of number of zeros by 2, you will find that first two samples are in error. So this is an important result, because when you want to get linear convolution using circular convolution, then you must add the correct number of zeros. Okay, now why was this so important? Because when we did the linear convolution of a long sequence with a filter impulse response coefficient which was much shorter, what we said was we will break up the long sequence into segments of length L. The length of the filter is P, 0 to P minus 1. Now, the linear convolution of these two, of this L point sequence with a P point sequence, should be L plus P minus 1. So, we know exactly how many zeros should be added to the sequence H of n. We know how many zeros must be added to each of these segments of the input data, x subscript 0 of n, x subscript 1 of n, and so forth. Okay, so basically, if we can summarize the steps that we have done, we took the original sequence x of n, we split it up into segments. Segment 0 going from 0 to L minus 1, segment 1 going from L to 2L minus 1, segment 2 going from 2L to 3L minus 1, and so on. So basically, the relationship is x of n is equal to the sum of all these segments of the input data appropriately shifted. So the output can be computed as the linear convolution between these segments and these and the impulse response coefficients. Okay, and we saw how we would take these individual segments, convolve. Each of these will produce a sequence L plus P minus 1. Then you go on to the next segment, take that segment, be careful of how you're doing the indexing, because there will be overlap between the two sequences. You take the second segment, convolve, you'll get another L plus P minus 1, third segment L plus P minus 1. So you can see that there is overlap. The green segments are showing the overlap between successive outputs. All of these are added together. So this method has got the name overlap add method. So what you're doing is you are breaking segments, computing the linear convolution, and then adding the outputs with the appropriate amount of overlap. Okay. Now, where does DFT come into play here? Using DFT, convolution using DFT. Okay, this is how we would do that. So this is the method which we call as overlap add method. Okay. Step 1, add L minus 1 zeros to H of n. That's the impulse response coefficients, and compute L plus P minus 1 point DFT. We'll call that as H of k. Okay, and this we store, because every step that we are going to store in memory. Every step we are going to use the same filter, so all the time we are going to recall this from memory. Second step, each data segment, okay, we call that as x subscript r of n. What we do is we add P minus 1 zeros. P minus 1 zeros, then this L plus P minus 1 point DFT. Okay, this will be XR of K. Okay, XR. Then step 3, we compute XR of K times H of k. We call that as YR of k. So this is where the DFTs are getting multiplied. So this will produce for us a circular convolution of XR prime with the zeros padded with the L plus P minus 1 point circular convolution with H prime. Okay, so basically H prime. So basically H prime of n, this will be x1 prime xr prime of n. Okay, this is the same as xr of n linear convolution with h of n. That's what we wanted to achieve. Through circular convolution via the DFT, we get this expression. This is what we are interested in. So step 4, we take the inverse DFT of YR of k. So YR of n is equal to IDFT of XR of k times H of k, and this is nothing but XR of n linear convolution with H of n. And then each of these segments you just have to shift and add. So step 5, y of n, the output is equal to summation r equal to 0 through infinity yr of n minus r l. Okay, remember each of these segments of yn, yr of n is of length l plus p minus 1, but you are shifting it only by l. So therefore, in this step, you will have both overlap and addition. That's why it's called the overlap add method. So let us go back and look at it one more time so that you are comfortable with it. We broke up the segments, broke up the sequence into segments. We wanted to compute the linear convolution of each of these segments with the impulse response of the filter. We appended zeros for both the filter coefficients and also for the segments. Took the DFT, multiplied the DFTs together, took the inverse DFT. So then what we got, because of the we added the correct number of zeros, we got the linear convolution of the segment with the filter. Now you add all these outputs, you get the overall output of the filter. Advantages: you don't have to wait for the entire sequence to come in, you can compute the output in segments. Second, the computation of the linear convolution in the time domain will require a certain number of computations. If you do it in the DFT domain, which we will now move from DFT to the fast Fourier transform, then we will get a very, very significant reduction in terms of the number of computations. So the advantage of doing the convolution using the DFT is the reduction in the number of computations. It's a very, very significant reduction, and we will just refer to what is the level of reduction in terms of complexity, so that then you will be able to appreciate what is going on there.